Hey there, science fans. Have you ever wondered what stuff is made of, like really made of? It's a question people have been asking for ages. We can see and touch things like wood, water, or even the air we breathe, but what are those things made of on the inside? This is where the study of matter comes in. Matter is anything that takes up space and has weight. And guess what? Everything around us is made of matter. Your pet hamster, matter. Your favorite video game, matter. Even the seemingly empty air is full of matter in the form of gases. To understand matter, we need to zoom in, way in, to the itty-bitty particles that make it all up. We're talking atoms. Atoms are like tiny building blocks. Just like you can use Lego bricks to build all sorts of things, nature uses atoms to build everything we see and interact with. Understanding atoms and how they combine helps us explain how matter behaves. It's like having a secret decoder ring for the universe. Back in the early 1800s, a clever scientist named John Dalton came up with a powerful idea, the atomic theory. Dalton's theory was a big deal because it helped explain a lot about how elements and compounds work. He gave us a framework for thinking about these tiny particles. Here are the key points of Dalton's atomic theory. 1. Elements are made of atoms. Dalton said that every element, like gold or oxygen, is made up of super tiny, unique particles called atoms. 2. Atoms of the same element are identical. He believed that all atoms of a specific element were exactly alike, like all oxygen atoms are the same, but they're different from hydrogen atoms. 3. Atoms are unbreakable in chemical reactions. Dalton thought atoms were like solid little balls that couldn't be split apart or destroyed during chemical reactions. They might rearrange, but they'd still be there. 4. Atoms combine in whole numbers. Dalton figured out that atoms join together in simple whole number ratios to form compounds. You can't have half an atom. For example, water is always 2 hydrogen atoms and 1 oxygen atom. 5. Atoms rearrange during chemical reactions. Dalton realized that in a chemical reaction, atoms aren't created or destroyed. Instead, they just rearrange themselves to form new substances. Now, let's talk about how atoms get together and what happens when they do. This is where stoichiometry comes in. It's a big word, but it's just about the amounts of stuff involved in chemical reactions. Think of it like a recipe for chemistry. 1. The law of conservation of mass. This law says that in a closed system, the total mass of the reactants, the stuff you start with, must equal the total mass of the products, the stuff you end up with. Basically, you can't create or destroy mass in a chemical reaction, just like you can't magically make a cake appear without using any ingredients. For example, if you burn a piece of wood, which contains carbon in the air, which contains oxygen, the mass of the wood and the oxygen used up will equal the mass of the ashes, smoke, which contains carbon dioxide and other gases produced. 2. The law of definite proportions. This law tells us that a chemical compound always contains the same elements in the exact same proportions by mass, no matter where it comes from. It's like saying a water molecule always has 2 hydrogen atoms and 1 oxygen atom, whether it's from your tap or a glacier in Antarctica. For example, water always contains hydrogen and oxygen in a ratio of 1:8 by mass. This means that for every 1 gram of hydrogen, there are 8 grams of oxygen. 3. The law of multiple proportions. This one's a bit trickier, but it basically says that when 2 elements can combine to form more than 1 compound, the masses of one element that combine with a fixed mass of the other element are in a ratio of small whole numbers. Think of it like building with Legos. You can use different combinations of bricks to make different structures. For example, carbon and oxygen can combine to form carbon monoxide and carbon dioxide. In carbon monoxide, 12 grams of carbon combine with 16 grams of oxygen. In carbon dioxide, 12 grams of carbon combine with 32 grams of oxygen. The ratio of oxygen masses in these 2 compounds is 16:32, which simplifies to 1:2. So why do we care about atoms and stoichiometry? Well, they're not just abstract ideas, they have real-world applications that affect our lives every day. First, let's talk about pharmaceuticals. Making medicines relies heavily on understanding how chemicals react in precise ratios. Stoichiometry helps pharmaceutical companies create drugs with the right amount of active ingredients to be effective and safe. Next, we have industrial chemistry. From making plastics to producing fertilizers, industries rely on stoichiometry to calculate the exact amounts of reactants needed to create products efficiently and minimize waste. And finally, there's environmental science. Understanding the stoichiometry of chemical reactions helps environmental scientists monitor and control pollution. For example, they can use it to calculate how much carbon dioxide is released by burning fossil fuels. We've covered a lot of ground, from the tiniest atoms to large-scale applications of chemistry, but the main takeaway is this. Dalton's atomic theory and the laws of stoichiometry are fundamental to understanding how matter behaves. They provide the framework for explaining chemical reactions and have countless applications in various fields. By understanding these concepts, we can predict how chemicals will react with each other, design new materials with specific properties, monitor and protect our environment, and develop new technologies to solve important problems. So the next time you look at a seemingly simple object, remember that it's made up of billions of atoms interacting in ways that we're still learning about. The world of chemistry is vast and fascinating, and it all starts with understanding the building blocks of matter.